Noaizir, and my teammates are Nur Azlani, binti Jamaluddin, and Nur Maisarah, binti Ramli. Today we are present our lab report on experiment 9, which was benchtop cooling tower. I'll go through first into the introduction of our lab. Cooling tower mainly used in air conditioning system as it was used to cool down the warm water from the chiller condenser, and this experiment was conducted to study the effect of different parameters towards the end state of properties of water and also the effect of cooling load on wet bulb approach. The experiment was divided into three parts, which different parameters were being tested, which were air flow rate, water flow rate, and also cooling load. Next, I proceed to the theory and background of our lab. Cooling tower operates by following first law thermodynamics, which was about the conservation of energy, and it was stated that the total energy of an isolated system is constant, where energy can be transformed from one form to another form, but cannot be created or destroyed. Energy that enters the cooling tower is in the form of hot water after being heated by the heater, where the other energy source were being negligible. The cooling load of hot water was the form of forced convection, by which ambient air was blown over the hot water and exited the cooling tower. Both the entrance and exit temperatures of the air and water were recorded. Since the specific heat relation does not take into account the percent of water in the air, a psychrometric chart is used to determine the enthalpy change between the entrance and exit air. To do so, the dry bulb and wet bulb temperatures of the inlet and outlet air need to be determined by using sling psychrometer. Then, the information obtained can be used to determine the enthalpies on the psychrometric chart. Once the enthalpies has been obtained, energy balance can be conducted on the system. Next, I will explain about the objective of our lab. First, to determine all end state properties of the air and water from charts and table. An application of the steady flow equation to a selected system to draw up energy and mass balances, which included in part 1 and part 2, where the parameters tested were air and water flow rate. Second objective is to study the effect of cooling load on wet bulb approach, where the different cooling load were used to fulfill the objective.
Hi, my name is Damar Sarah and my matrix number is 196309. I will be explaining how the machine works and the operating procedures. So as you can see, this is a figure of the benchtop cooling tower. There is the temperature sensor over here, distributor, temperature sensor again, fan, heater, incline manometer, water flow transducer or the control valve, the temperature indicator, and the makeup tank. So this figure shows the inside of the benchtop cooling tower. So I'll be explaining how does this machine works. First, the water in the load tank over here will be pumped into the control valve, and then it will goes into the cap column. So this cap column has the temperature sensor over here, so it will detect the temperature, and then the water will be flow into the pack column, the top pack column. As the water flows downward into the bottom of the packing column, the water will be cool as a result of evaporation from the total flow. So the water from the bottom pack column will then goes into the basin, and then it will flow past thermocouple and goes back into the load tank so that it can be reheated for recirculation. So as the water in the load tank decreases, because of the evaporation, the float valve will be opened so that the water in the makeup tank can goes into the load tank. So So under the conditions, the rate at which water leaves the makeup tank is equal to the rate of evaporation and plus any small airborne droplets in the air discharge. And then for air circuit, it's the same thing except that we will be changing the rate of air from this air inlet of at the fan.
Assalamualaikum, my name is Nur Azliani. My metric number is 198681. So I will explain about how we manipulate all the parameters in this experiment and the response that we have been observed. So this is the result data, and for part 1, variable airflow rate, which is in this experiment, the cooling load is set to be constant, and we manipulate orifice differential, which is airflow rate. And from this experiment, we want to observe the makeup quantity to determine the rate of evaporation. For part 2, which is different water flow rate, for this experiment, we manipulate the flow rate and we observe the cooling range to know the mass transfer and heat, which is from temperature T5 to T6, and we want to observe the makeup quantity and the rate of evaporation. So part 3, the difference of cooling load, and for the cooling load we adjust from first test number is 0 kilowatt. For the second test we add to 0.5, and for test number 3 we set to 1 kilowatt, and we want to observe the makeup quantity that is determined on the rate of evaporation. So for data analysis and discussion, for specific enthalpy and moisture content, we take the number from the psychometric chart. For experiment part 1, which is the airflow rate, is the one that we manipulate, and we can see for the inlet specific temperature, it shows the increment, and the outlet specific enthalpy, there is uncertainty in the value of enthalpy. For the moisture content, it is also show the uncertainty of the value. And for part 2 of the experiment, for the specific enthalpy inlet, it shows the decreasing number of specific enthalpy, but for the outlet, it shows the increment of the enthalpy. For moisture content, inlet moisture is decreasing, but for the outlet, it shows the increment of moisture content. So for the question, why water need to be always added to the system? This is because the makeup water supplies need to be recirculated due to evaporation, which is water that discharge to prevent the accumulation of the solid in the cooling water. The makeup water system provide the replacement of water via a mechanical float ball and valve assembly, which measures water depth in the cold water basin. And the second part is, what is the effect of airflow rate on the makeup rate and water outlet temperature. So in part 1, the makeup quantity shows uncertainty, which is the makeup quantity from 16 gram per second to 17 gram per second is decreasing, and the water outlet temperature is increasing, but from 17 to 18 gram per second, the makeup quantity decreasing and the temperature outlet increase. The uncertainty occurs in some areas, which is one of the source of contributed the area is the ratio of humidity in the experiment. If the level of humidity is high in an area, then the makeup water quantity will be less because the surrounding is already wet and it does not need a plenty of water to compensate the losses.
Next, we proceed to the conclusion of the lab. First, the faster the flow rates of the water and air, the lesser the effectiveness of the cooling due to the shorter time to transfer energy to the air. Second, the higher the cooling load, the lower the rate of evaporation due to the higher power. Lastly, for the recommendation, these errors were propagated through the calculations and significantly impacted the result. Heat losses through natural convection to the surroundings were found to be minimal and have a negligible effect on the energy balance results. The effects of such errors could be decreased through increasing the precision of reading and instrumentation equipment and through the installation of the cooling tower and pipes. So that's all from us. Thank you.